Okay, so we're going to cover the concept and the motivation behind analysis of variance just for the one-way case, which is also single factor. So there's one variable, which is a categorical variable with multiple levels. We'll go over the necessary assumptions, carry out the analysis of variance F-Test under the assumption that under the null hypothesis that several populations are equal, and give you just a bit of practical experience interpreting the one-way ANOVA table and doing so-called post-hoc corrections. Oh, good. Thank you, Sarah. Okay, so just to recall an example from a couple classes ago when we were doing the independent samples t-test, so the t-test for two independent samples. One of the examples we did was this cell phone and control, where there were two groups, and we were looking at response time to a stimulus for people not using a cell phone and using a cell phone. And in the t-test example, we were testing the null hypothesis, either that the difference between these two mean response times was 0, or that the two are equal, and the alternative hypothesis just that they're not equal. And now, the extension we're going on today, it's really an extension of the same problem, but to where we have multiple groups. So suppose that instead of just cell phone use, we were comparing someone not using cell phone to someone using voice only, or to someone who is using some combination of voice and text or email. So there isn't just one thing that we're comparing to control, there are multiples, or any sort of situation where we have a categorical variable with multiple levels. Just start with a very simple toy example here, and one that you could work out yourself if you want to, using a calculator even. Here's an example, made-up example of 3 training programs. Say these are training programs for seeing how fast you can run some length of distance, and then we, after putting 3 subjects each through each of these 3 training programs, we measure their times. So this would be data. Here are the 3 training methods, 1, 2, 3, and the 3 individuals for each method, and the length of time that they took. And this is an example of where we're going to use analysis of variance. So looking at these numbers and some descriptive statistics in SPSS, you can summarize them, the value of the time according to the variable method, and get your n and a few descriptive statistics for each. And these are the values, the mean and standard deviation, that are going to enter into the analysis of variance. So the null hypothesis is going to be that the population means for an infinite number of people trained by each of these 3 methods is the same. And here's what we are observing for this small sample of n equal to 9. Here's a box plot of this little data set. So just visualizing the 3 times each for the 3 methods. There are only 3 data points here, so you can actually see all 3. The middle data point will be the median point here, and the smallest of the 3 and the largest of the 3. So you can see right away right here that it looks like there is some difference between these 3 methods. The question will be, is that much difference enough to have just occurred by chance, or is it evidence that this is in fact, results in slower running times. So you could just use t-tests for this case. If you were going to do that, you might compare method 1 to method 2, method 1 to method 3, and method 2 to method 3. So there are 3 different t-tests that you would do. And with each of those, you would control the type 1 error rate alpha, for example, at 5% for alpha equals 0.05. But note, if you do that 3 times, the overall probability in each one, you have a 5% probability of type 1 error. Across all 3, your chances of having one type 1 error is going to be more than 0.05. So instead of doing that, we're just going to do one test that considers all 3 of these. And that one test is going to have a type 1 error rate of 0.05. So with the analysis of variance, specifically the one-way analysis of variance, this is about, we're going to be comparing the means of several populations. So with 3 methods like this, it's mu1, mu2, mu3. And again, the problem with using multiple tests between each pair is that as you keep on doing more tests, you end up inflating your error rate. And as an example here, just to do a little calculation, in each one of your tests, your probability of having a type 1 error would be 0.05. Your probability of not having a type 1 error is 0.95. Your probability of not having a type 1 error 3 times in a row is going to be 0.95 cubed. So that's your probability of never having any type 1 error, and your probability of having it at least once is going to be 1 minus that, and it's 0.14. So even though you set alpha equal to 0.05, you end up with an overall type 1 error rate of 0.14. And this is a problem that we refer to as multiple testing. And as you do more and more comparisons, this problem gets more and more severe. If we had 6 groups, this would be getting up, it would be more than 50% of having at least one comparison in there that is significant. So the basic idea here is that we're going to be looking at several groups and considering whether the differences that we see between groups is larger than the difference that we see within groups. So in an example like the left, the between group differences being about this much looks kind of similar to the within groups difference, and it's going to be hard to tell a difference. Whereas in a case like this, where the within group differences are smaller, even for those same size of between group differences, this is going to be much stronger evidence of there being a difference in the population means for these 3 populations. So to look at it in terms of histograms or probability plots, here are 3 different population distributions, 2 of them about the same, 1 of them quite different. And you can imagine in this case where there is a lot of overlap between these 2 distributions, it's going to be hard to distinguish the difference. In this case, where there is not so much overlap, it's easier to tell the difference. So the key idea here is that our evidence against equal means has to do both with the size of the difference between the means and with this variability within the groups. And it turns out it's actually just a simple ratio of those 2 things, as I'll show you later. In that sense, it's the most intuitive test you could possibly think of for doing this test, and it turns out also to be probably the most useful. Which is great. Okay, so just to cover the notation here, it's going to be consistent with everything we've done. population means, we'll use mu1, 2, up to mu g, where g is the number of groups. And standard deviations, the same thing, sigma. And the sample statistics, oops, I forgot to write in the means here. That's because I always have a hard time. This would be x1 bar, x2 bar, dot, 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 xg bar here. I would have just written this in if, then maybe I can do that. No, I'll let you write that in. And the standard deviations, S1, S2, up to SG. Okay, so the null and alternative hypotheses. Your first step in performing any of these tests. Just to show you the continuation from things we've been doing already before. In the case where we had one population and we were comparing that to a theoretical mean under the null hypothesis. This was the one sample z-test, the one sample t-test. It was the mean of that population equal to mu0, the theoretical mean under the null hypothesis, and the alternative mu not equal to mu0. In the case of two populations, it was that the means were equal, and the alternative hypothesis was that they're not equal. This we covered under the two sample z-test, and I put here one-way ANOVA because you actually can do this with using one-way ANOVA as well, and it turns out to be equivalent. But when we have multiple populations, this is where we really are into the realm of one-way ANOVA, and the previous methods aren't going to work. The null hypothesis here is that all of the population means are identical. There's no difference between them, and we normally use this with 3 or more populations, even though you can also use it with just 2. And the alternative hypothesis, and this is similar a little bit looking back at the last class with the chi-squared test, is just that there is a difference somewhere. It doesn't tell you where the difference is, just that the null hypothesis is not true. So it might mean that there is one population that's different from the others, or it might mean that they're all different from each other. Okay, the assumptions. Like with the t-tests, we make the assumption of normality, that the data are approximately normally distributed, or that we have a large sample size. Large sample size forgives all. If you have a large enough sample size, it doesn't really matter. Here are some rules of thumb for the one-way ANOVA with 3 groups. This has only a kind of limited usefulness because you're going to be doing one-way ANOVA with more than 3 groups, and this isn't going to help. But it gives you kind of an idea around if you have anything with n greater than 40, this is a large sample size. Of course, if you have more groups, so that you have, we're just talking about, if you have more groups here, then generally you might need a slightly larger sample size. But 40 is a pretty big sample size when it comes to ANOVA. This is a new assumption, homoscedasticity, and this is similar to the equal variances ANOVA that we did before, where we assume that we have a pooled standard deviation between the 2 groups. We always make this assumption with ANOVA. So that means that each of your populations has the same standard deviation. By the way, I don't recommend that you use things like Bartlett's tests, or there are tests that you can do to detect variations from homoscedasticity. I have heard this called the equivalent of sending a little rowing skiff out on the ocean to test whether it is calm enough for an ocean liner. That's because the Bartlett's test, it's going to be very sensitive and detect any difference from non-normality, whereas the ANOVA is very robust, and those tiny little changes, those tiny little waves really don't matter to ANOVA. And to make it worse, the larger your sample size, the more powerful this test of normality is going to get. So if you had n equals 10,000, Bartlett's test will give you a tiny p-value if there is any difference in sample size. But with the larger sample sizes, the less it matters for ANOVA. So instead, this is kind of a rule of thumb that people use, that if they don't differ by more than a factor of 2, then you're fine. So as with the assumption of normality and as with the T procedures, the F-test and one-way ANOVA, it's robust and it's also conservative. So if you violate this, you're going to be less likely or less able to reject the null hypothesis. So you're very unlikely to it's not going to inflate your type 1 error rate. Does that make sense? Does everyone know what that conservative thing means? Yes? Sorry? So the question, I think, was that there are different assumptions depending on which test you decide to use, and in fact, the outcome of using different tests can be different. I have more or less been giving you only one method to analyze each situation, even though there are multiple methods. So as an example here with the ANOVA, there are equivalent families, and I'll try to summarize this in our last class too. There are equivalent so-called non-parametric tests, which you can use under the exact same situations, which will give you a different outcome for the exact same data. But for this, as far as you're concerned in this class, if you have a continuous response variable and you have a categorical second variable or predictor variable that you want to test for association, and your categorical variable has 3 or more levels, then ANOVA, one-way ANOVA, is the only test that you have available to use. So you're not going to go instead and choose the t-tests and get a different outcome. ANOVA is the correct test to use. So your point that using different tests can give you a different outcome is true, and that's why it's important to choose an appropriate test for your objectives and for the data that you have. But it's worth noting that if there are more than one appropriate tests, chances are they will give you similar, if not identical, answers. Like the case that I mentioned here, with 2 samples, you can use a t-test or you can use an f-test, and they actually give you identical answers. Another one came up in email before about how you could, with a 2x2 table, contingency table, you could use the chi-square test, or you could also use a proportions test with z, and it turns out those are equivalent also. So it's not just that you can get the answer you want by choosing the right test. You choose the test based on the data and your objectives, and then interpret the results of the test. There's only so much leeway. Does that sound good? All right. Okay, so here, in case you want to do a hand calculation of the analysis of variance, if you want to try it out with this toy example we gave, just to really see how it works, here is how you do it. There are these two S squareds. The within, so remember in the in the box plot or those normal distributions that I showed, this S1, S2, and S3 would be the sample standard deviation that you count within each group. So S1 would be, in this simple example, would be based on 3 data points, the ones for group 1. S2 would be based on the 3 data points in group 2. And S3 would be based on the 3 data sets in group 3. And all this is just a weighted average of these 3. So this is the degrees of freedom for group 1 and the degrees of freedom for group 2. So all it works out to be is you multiply each S squared, the variance, by the degrees of freedom for that group, add these up, divide by the total number of degrees of freedom within groups, which is N1 minus 1 plus N2 minus 1 plus N3 minus 1, which just turns out to be the sum of them minus the total number of groups. And then you calculate this between group standard deviation, which is just, it's again a weighted standard deviation, but here instead of calculating the standard deviations within the groups, you take the mean of the group minus the so-called grand mean. That is the mean of all of all of your data points. And each one of those, you weight it by the sample size, so you multiply it by the number of samples in that group. You add them up and divide by your degrees of freedom for that variance, which is the number of groups minus 1. So I'll show you graphically a little bit, give you a little bit better idea of what these mean, since not everyone is that into equations. What we're doing here is splitting up the total variability in the sample sizes into that happens between groups and that happens within groups. And this F statistic is just the ratio of those two. So the between group, or this is sometimes called the numerator degrees of freedom, or we talk about the degrees of freedom in the numerator as being for the numerator and for the denominator, but this is also often just called the between groups mean sum of squares or variance, and the within groups sum of squares or variance. I wonder if this might be a good time to show you. I wanted to show you an example here from a web page that I think is kind of helpful. I'm going to switch. Where's the... Okay, maybe I will skip this. Oh no, here we go. Visual ANOVA. Okay. If you Google Visual ANOVA, by the way, you will get this page as the top hit. Oops, and I seem to have. There we go. Okay. So here's a representation of 4 groups, and this is just showing where the data are. So this is the length of this is the variance, and the mean of it is right in the middle. And this just shows you a calculation of the F statistic. So in this case, the variation between is actually 0. They all have exactly the same mean, and so the F is 0 here. But as soon as you go and move one of these, you start getting some variation between groups, and you see this numerator start to grow. Notice that as I move this around, the mean squares, so this is the S squared, within groups doesn't change at all. I can move all of these around. It changes the numerator, the between group mean square, but it doesn't change the denominator. It also moves around this grand mean, which is the average of everything. Yeah, question? Yes. So the one on the left here has a bigger standard deviation than the others. That was the question, and would that violate the assumption of the ANOVA? This is just as representing a sample here. So yeah, it's the population. The assumption is that the population standard deviations are the same. You'll always see some variation in the sample standard deviations. But again, this much difference, this is like less than a factor of 2. It would not be something to be concerned about at all. Now, as I start changing one of these variances, notice how the denominator, the within groups, is getting smaller, but the numerator is staying exactly the same. That's because all that goes into the calculation in the numerator is where these means are, and I didn't change that. But I am changing the within group variance. Okay, so I hope that kind of makes clear what this within group and between group variance is. And that's a really important concept, not just for one-way analysis of variance, but for the t-tests and for all sorts of other analysis of variance that you could end up getting plunged into in the future, that it's really, you're interested in the amount of variation between groups relative to the amount of variation within groups. Any questions about this, or anyone want me to move the sliders around in some other way? Okay. I'm going to go back to the slideshow. Okay. So continuing with the calculation of the one-way ANOVA F-Test, I showed you how to get the within group and the between group variances or mean squares. The other thing that you have to know about is the degrees of freedom. These are the numerator and the denominator, or the df1 and df2 degrees of freedom. And both of those affect the F distribution. So things had already gotten kind of bad with the t distribution, in that there was a different one for each number of degrees of freedom, and the same with the chi-square distribution. It's even worse now because the F statistic has 2 different degrees of freedom, and both of these affect the both of these affect the distribution. So the table of F statistics, or the table of the F distribution, which you can get in Agresti or anywhere else, is even more coarse than it was for the chi-square or the t distribution, because there are these two different degrees of freedom. Here's just an example of how it varies with the degrees of freedom. It varies a lot, but you'll note that for few degrees of freedom on both sides, it's a lot of the probability is down here close to 0, but it has a long, long tail. So it, just with these small sample sizes, the F statistic can range up to pretty large values just due to chance. Whereas with a larger sample size like this, D1 equals 100, D2 equals 100, it drops off to it. First of all, it has a higher peak value, but then it drops off to 0 much more quickly. So both of these affect the distribution in different ways, the DF1 and DF2. So as with the chi-square test, we only ever do one-tailed tests here. We only ever look under the right tail of this distribution, even though the alternative hypothesis is naturally multi-sided. It's not like the t and the z tests where we had to think about two tails. As a side note of interest here, as you do get more degrees of freedom, this probability drops off to the left here, especially as you get a larger numerator degrees of freedom. And it's very unlikely that you have almost no within group or no between group variance for several of your groups. And there have been cases of people catching scientific misconduct, falsified data this way. It's happened with the chi-square test and with the F-test. Someone making up data without understanding these distributions and actually making their data a little too perfect. So they had, there are several groups that they thought should be the same, and due to removing data points or whatever, they ended up being way too much the same than you would expect, even just by chance. Because you can imagine that if you have a certain amount of variability within your groups, that same variability should cause some difference between the groups. And they would only end up with exactly the same mean if the data were, either if you're very unlucky or if the data were falsified. This is a plot that that SPSS will show you, and I did actually figure out how to get this. It will plot for you the means for each of the groups, which is, I think it's probably not as useful as the box plot, but it's just another way of seeing these differences. And for me to show you here the variation, this is back to that simple training programs example, how the between group differences and the within group differences. So these red arrows here are each of the between group differences. So if you do analyze means and the one-way analysis of variance, you'll get a table something like this. And this is a very important table to know, to get used to reading. Every statistical program will give you something similar to this, the analysis of variance table. And the key things, I'll go through all of it, but the key things I want to show you here were the degrees of freedom that we had. There were 3 groups, so 2 between groups degrees of freedom, and 6 within groups degrees of freedom. That's because in each group there were 3 data points of 2 degrees of freedom, 2, 4, 6, to add up to 6. These sum of squares here, this is just the taking the difference, so between groups, the difference between each group mean and the grand mean, squaring those, adding them up. And the mean squares is just this divided by the degrees of freedom. So here 248 divided by 2 is 124. And this is the S between squared, and this is the S within squared, also just the sum of squares divided by the degrees of freedom. This total one, by the way, this is what you get if you just ignore the groups and you just look at all of the data points as one group and take their differences from the grand mean, and you'll notice that if you add up the between groups and the within groups, you should get exactly the total sum of squares. So it's really just breaking down your variability into that happens between groups and that happens within groups, and those add up to the total. So these mean squares, the S squareds, the ratio of these two, the between groups, 124, divided by the within groups, S squared, that's the F statistic. If you go 124 divided by 11, you should get 11.273. And the p-value is what you would get by calculating the area under the F distribution to the right of this value. If you take the distribution with degrees of freedom equal to 2 in the numerator and 6 in the denominator. Of course, you're not going to be able to calculate this accurately with a table. You have to get this from software. What you could get from the table would be an approximate critical value, and you would find that at 0.05, the critical value would be quite a bit less than this, and that would work as well. So these two things are the key output of the table, and the ones that probably you would report in a paper or in your project for if analysis of variance were your main result. The F statistic is 11.27 on 2 and 6 degrees of freedom with a p-value of 0.009. So this tells us that at least one of those methods is probably different from the other two, but it doesn't say which one. I haven't usually done this, but I went since I thought I would go ahead and tell you how to do this in SPSS just for reference. So we don't know which one, and that's where the so-called post-hoc tests come in. Post-hoc tests are a way to put confidence intervals on the differences between each of the groups and to say where these significant differences are likely to lie. And take note that you should only do these if you get a significant result for the F-test. If your p-value from the F-test is above your significance level, then you just stop there. You say there are no differences between these groups, and you don't do post-hoc tests. If you do get a significant p-value from the analysis of variance, then you can go on, if you're interested to, and do the post-hoc tests. Here, you'll find under the analysis of variance, under the options, there are a whole bunch of options for post-hoc tests. I'm just summarizing a few of them here. The Bonferroni one is not the one that people usually use, but it bears mentioning because this is an extremely versatile test. You can use a Bonferroni correction in almost any situation, and it is very conservative. So if you use the Bonferroni test to correct for multiple comparisons, then you can be quite confident that any of the comparisons which are still under your alpha after doing that are significant. But you can have a higher type 2 error rate with the Bonferroni correction. The one that people usually use after a one-way analysis of variance is this Tuckey method, and that's generally the best method for doing all the pairwise comparisons. So every possible pair of levels in your categorical variable. These other two I just mentioned because they have special uses which are nice if you happen to want to do that. The Dunnett method, if you have one control and several treatments and you only want to compare each control to the same treatment, then it's going to be a bit more efficient than the Tuckey method. And the Sioux method for comparing everything to the best treatment. So if you if you take the group that has the highest mean and then you want to compare everything else to that, then this is the best method for doing that. There are tons of these methods. I think it's unlikely that you're going to need to know more than this. These are fairly generally useful. Yes, question. You could, yeah. So the question is, can't you just do a t-test now between each of the means? You could do a t-test between each of the groups as long as you still corrected those p-values for multiple testing. You should just be aware that the confidence interval then that you get for, if you look at your largest difference and calculate a confidence interval, that confidence interval is going to be a bit smaller than it should be, because you're not accounting in any way for the multiple testing when you do the t-test. So in the case where you had like 6 groups, you have, what does that work out to, like 15 tests like that. If you take your largest difference and do a t-test, it's going to give you a confidence interval that's quite a ways away from 0. And if your F-test was significant, then after correction, that confidence interval probably still shouldn't contain 0, but it's going to be a wider confidence interval, and it'll be a bit more realistic of your real estimate between those two groups if you were to go and do another experiment that included only those two. And by the way, I think that's called snooping, when you just pick out the largest difference you see between groups and only test that difference. And it's not an illegal thing to do, but there are methods that will correct your p-value and your confidence interval for cases where you're doing so-called snooping in your data set. Okay, another question? The question was, given a data set, could you compare chi-squared tests with could you compare chi-squared to ANOVA test? The only way you could compare chi-squared to an ANOVA test, so ANOVA test, you have one continuous variable and one categorical variable, whereas with chi-square test, you have 2 categorical variables, so you can't directly compare them. The only way you could directly compare them, for example, if age were your continuous variable, you would have to create discrete categories of your age variable. So, 20 to 30, 30 to 40, 40 to 50, like take a continuous variable and turn it into a categorical variable. Then you could use a chi-squared test. But without altering your data, you can't just choose between chi-squared and ANOVA. But that reminds me, another thing that I will do next test is make an overall table of variable types and what your options are for tests to help you to choose between all of them. Okay. So any of these tests, when you select to do them in SPSS or your other software, they're going to give you confidence intervals on the difference in means. Interpretation of these is going to be just the same as you've done before with confidence intervals, because they're going to be corrected for multiple testing so that you can interpret them directly. So they provide the range of plausible values for that difference in population means based on your data set. And if that difference does not include 0, then you infer that the population means are different at your given level of confidence. So here's an example output for that learning example with Tucky's on a significant difference method, the one that you're probably usually going to use. And you'll see for each, so for method 1, it shows you the comparison to methods 2 and 3. For methods 2, it compares to 1 and 3. And then method 3, this is actually just repetitive with the other two. So for each one of these, method 1 to 2, it gives you the mean difference, I minus j. So this is the mean response time for method 1 or minus the mean time for method 2. That difference is 2. Standard error, significance level, and the lower and upper bounds. So the significance level is above 0.05. The confidence interval contains 0, so that's probably not where the difference lies in this data set. But 1 minus 3 has a much bigger difference, about the same standard error. The significance level is under 0.05, and this confidence interval does not include 0. So we would conclude that there probably is a real difference at the 95% confidence level between methods 1 and 3, and that the mean for method 3 is higher because the method 1 minus method 3 gives a negative value. That's how you interpret these tables. And you can set different significance levels, and depending on what significance level you set, this will be the same, this will be the same, everything will be the same up to the lower and upper bounds. If you set a different significance level, these are going to change. But all of these will remain the same. And just to plot those in another way, I can't actually figure out how to make a plot like this in SPSS. I know how to make it in R, but where you actually plot all of the confidence levels for the differences together. If you did it in this case, this is just a reminder back from the Boxplot where we saw that number 3 had a higher mean than 1 and 2. Here is what the confidence intervals look like. So the difference between 1 and 2 crosses 0. They're not very different. 1 is slightly higher than 2, so the center of the confidence interval is above 0. And for 1 minus 3 and 2 minus 3, the difference is going to be negative, and the interval doesn't cross 0. Okay, so wrapping things up here and summarizing, the F-test is a test of significance in the case where you have a continuous variable that is grouped by a categorical variable, and where that, especially where that categorical variable has 3 or more values. And the F-test tests the null hypothesis that each of these groups has identical means in the population. And like the chi-squared statistic, we use only the right tail of the distribution, but the alternative hypothesis is inherently multi-sided. There's any number of different ways that you can deviate from the null hypothesis. There were three assumptions we covered: the normally distributed populations. Oops, this should say homoscedasticity. I'm sorry. Maybe I will. I'm going to change that right now. Here we go. Homoscedasticity and independent samples, which has the independent samples or the randomization has slightly different meaning depending on whether it's an observational or an experimental study. But the point is that each of those groups is independent. We don't have the same individuals in two or more groups, and they are either sampled randomly or assigned randomly. And if the F-test is significant, then you can use these post-hoc tests to find where that difference is.